Okay, so does anyone know what recursion is?
Having a function call itself.
Yeah, having a function call itself, exactly. Is that all that you need? Well, I guess that's a tough question. Is that all you should have?
Probably not, but that's where I am.
Okay.
You should have a base case where it stops, the recursion stops.
Okay. Yeah, so you should have a base. So let's say we have a function that calls itself. Let me share my screen. So the minimum, like I guess the absolute bare minimum, as I think I'm saying, was that, let's see. So we do something like, we do. Okay, so I try running this and it prints out high like roughly 1,000 times. And then I get a recursion error. Recursion error, maximum recursion depth exceeded while calling a Python object. So I can do this and it works, but it's kind of like having an infinite while loop or something like that. I could do while true and then print high and it will just, actually, it won't stop. It'll just keep going until my computer blows up or I stop it. And Python could allow this to keep going until your computer blows up, but it stops you. So we know about the call stack. So if I put a debugger, if I run the debugger here, and I step through this, we have the call stack on the bottom left. So we start off, it's kind of the basic environment, and we call rec, so that gets added to the stack. And then we call rec again, so that gets added to the stack. And we keep calling and it keeps getting added to the stack. And eventually what would happen if Python didn't have this built-in maximum recursion error is that we would run out of memory, actually, because all these stacks require memory. So as Cindy N was saying, we need to have some kind of base case. We can call recursive. Yeah, this might be a little tougher to show here, but so what we need anytime you have you want to write a recursive problem, what you need to think of is, what is the case where I keep going? Where is the case where I keep recursing? And what is the case where I stop recursing? So you need to have those two things figured out for any recursive problem you have. Okay, so I'll say that so we typically will do these things with loops. So looping and recursion are two different ways of solving, 9 times out of 10 for solving the same problem. You can basically, if you can use one, you can use the other. Although there are specific cases where one or the other is maybe more a more obvious choice. But you can, just for simple loops, you can easily use recursion. And there are functional, so we talked a little bit about functional programming. One of the ideas of functional programming is that you don't use loops. The reason for that is because you don't want to reassign something to the same variable. So if we have a for something like this, in Python, this I is going to get repeatedly reassigned to, right? So first it's going to be 0, and then it's going to be 1. So functional programming doesn't like to do that. So they don't like for loops. So they want to use recursion. So we can actually create something that's like a for loop, just using recursion. So let's see if we can collectively write a function that will print from a given number down to 0. So I'm going to write def. It's going to take in a number, and it's going to do some stuff. So how can we go about doing this? So what are the 2 things that I always need anytime I have a recursive function?
You need a stop point, because otherwise could it go infinity down to negative numbers?
Yes. So we need a stopping point, or the usual term for that is base case. So we need to have our base case. And what do you think our base case would be, Cindy?
Assuming 0.
Yeah. So if num is 0. So we don't know what to do quite yet, but that's fine. So I think we have our base case. We know that if the number is 0, then we need to stop recursing. So what if it's not 0?
To call the function again.
Okay.
And you should modify the num,
Okay.
like subtract 1 from it or something.
All right.
Is pass the correct way? I assume it is because you're using it instead of break.
I'm just pass is just kind of like a dummy value,
Okay.
so I don't get red squiggly line. So pass is basically just a placeholder right now. So what should we actually do if the number is 0? Well, okay, so let's say that what we actually want to do is print every number starting from whatever the number is down to 0. So we're going to need a print statement somewhere.
Would we just do print num above the base case?
Okay, you do that. All right, so we have our, so someone walk me through.
Well, before we do that, shouldn't the countdown calling the same function again, shouldn't that be in an else?
It could be, it definitely could be. It depends on what we're doing here. So we haven't quite figured out what we're doing here. So let's someone walk me through step by step what's going to happen, and then we'll figure out what we should do for our base case.
Okay.
Anthony, you want to do it?
Okay, so line 12 is going to call our function with the parameter of 4. Then line 1's where our function is, so it's going to take 4. It's going to go down to 3, and it's going to print whatever number we have. If the number comes out to be what?
Wait, so okay, so num is 4 now. So then I print 4, and then what?
Then so it's not 0, so we're going to skip over line 6.
Okay.
Then we come back down to line 10, and then we're going to call our function again with the value of num minus 1, which will be 3 this time.
Right. So we go back here. Num is 3.
print 3,
Okay.
skip, call it with 2,
So 2,
print 2, skip, call it with 1, print 1, skip, call it again with 0, print 0, and then we come to our base case.
okay.
And right now, I guess it would just stop and then not do anything else because we told it to just that it's good.
So how do we stop the execution of a function?
I think it's break.
Okay, does anyone have any ideas?
Return.
Return. So what is break for?
Break is for exiting the loop.
Yeah, so if this were a while loop or a for loop or something, then we use break.
Okay.
So looks like this works now. So it starts at 4, 3, 2, 1, just exactly as Anthony said. And then when it gets to 0, we hit our base case and it returns. So let's look at the debugger. We can see the call stack. So we first call it. You can see that num is 4. It prints 4 down here, and then it calls the function again. We run through, we see the call stack building up. We'll keep going. The call stack keeps building up. And we can actually look at all of these stacks, right? Do you see the value of the numbers change? So all of these stacks is basically like a snapshot of what's happening when it's called. So in this stack, num is 4. In this stack, num is 3, num is 2, num is 1, num is 0. So these stacks, contain information about the execution context, which is why you'll run out of memory if you have an infinite recursion. Okay, so this next case, we're going to hit this conditional, and then it's going to return. So what happens when this function returns?
Did we just tell it that we're done using it? If there was a return value, it would spit that out. But then, like, under the hood, does that just mean the function has served its purpose?
Yeah. So it means the function is going to serve its purpose. So what happens to the call stack?
Gonna pop the things off the stack one by one.
Yeah. So we kind of we were adding stuff to the stack. And if you remember how stack is a particular data type, it's first in, last out. So if I do 1, 2, 3, I have to remove it 3, 2, 1, right? So the call stack works that way. So we have all these function calls, it's stacking up, stacking up, stacking up, and we have to unwind by just taking the first one from the stack. So we'll pop off, we'll start popping off the stack. So that first one gets popped off, next one gets popped off, they'll get popped off, and then we're back to the rest of the file. So again, the basic idea is that if you have a recursive solution or recursive function or whatever, you need 2 things. You need a base case. You always need 2 things. That's the first thing you should do when you think of recursive function. What is my base case? What is my recursive case? The base case will need to stop the function. The recursive case is whatever you want to keep happening. Okay, and then there are some limits. So we saw that when we had an infinite loop, we got this error, right? Which is actually it's configurable in Python, but Python could just let you go forever, but you would run out of memory, so it stops you from doing that. What if we did something like 1,000?
Is that going to get mad because it was stopping you at like 990 last time? So would it stop you at 990 again?
Yeah, let's see. Whoops. Let's see what happens. So we actually get the same error we had when we were just doing infinite recursion. So Python has, it's capped basically. So other languages will handle this differently. Python, if Python were a more strictly functional language, then this wouldn't be a problem, basically.
Can you override that?
Yeah, I mean, it's a configuration. I don't know offhand how you would do that. I've never actually tried doing it. But yeah. So there's nothing in Python itself that prevents this from happening. It's just, you know, Python doing your computer a favor. Okay. So that's the basics. Let's look at another case here. Well, okay, so that's count down. What if we want to count up? Let me collapse this. How could we write this one?
We need a stopping number in the as an argument in the function.
Okay, so let's say num, we'll call it goal start, something like that.
Yeah, so we can put our print inside of the recursive case, and that'll handle it.
Can you say it again? So are you talking about instead of having these two parameters?
Yeah, it's just another way of doing it.
Can you talk me through that?
Yes. So we can say if num is equal to 0,
Okay.
then we print num. And then we can say else. And we call count up again with num -1. And then after that, we print num. Or in this case, we're calling it goal, so it would be.
Oh, right. Sorry.
I'm used to just thinking num.
So we have a countup function. So let's walk through it. So if we give it 3, if num equals 0, nope, else countup. So this will be 2. We'll print 2, and then we'll call this. It's not 2, so it keeps going, and then it's 1, and then it prints again, and it keeps going, and it's 0, and then it prints num, and it will. So what will happen on the last iteration?
So on the last one, 0 will be printed, and then it'll return to the previous item in the stack, which will be 1, and then 1 will be printed, and then it'll return to the case where num is equal to 2. So the last item in the stack will be the first one to print, and it'll unwind kind of like that.
Okay, so I think in that case, I think we'll have to return this.
Oh, it's since it's printing it, we won't have to return it.
Okay. me. Okay, so this is yeah. So this is one way of doing it. This is probably the best way of doing this. Where you, so at the end, this will return none. But it's going to get down to the base case first and then unwind. So typically recursive solutions will work like this, where you kind of build up a solution and then you actually implement it in reverse almost. So we have a count up. So I wanted to show you something else. So we'll keep this here. So this is good. I want to show you something else using default parameters. So we'll do pass. And we'll start at 0, let's say here for now. So we have count up. We're going to start at 3, or sorry, this is count up should be the opposite. Yeah, okay. So we'll start at 0 and then we'll count up to 3. And we want, so the base case in this instance would be when the goal, or when start equals 3. So if we're incrementing start by 1 every time. So if start equals goal, let's return. We could do an else, and then we'll say print start, and then we'll call count up, and we'll pass it the goal, and then start +1. So if we want to count from 0 to 3, we call this is not equal, 0 is not equal to 3. So we keep going, we print out 0, and then we call with 3 and 1. These are not equal, so we print out 1. This will be 3 and 2. We call it again, not equal, so print 2. We call it again with 3 and 3. They're equal, so it returns.
If you want it to print out 3, do you need to add that into the first if?
Yeah, so I mean, you would probably see if this. So it starts at 0 and then increments. So I think this should do it. But there's maybe an issue. What if we don't want to force the caller to give us a starting number?
You could put start and then equals 0 to have it default to 0.
Yeah. So the caller doesn't need to know about this. Is basically internal. So this is a problem that I wanted to get at, is that if we have a recursive function and we need to build up, we need to pass information from one function call to the next. one solution is to use a global variable or something like that, right? So we could have start out here. Whoops. Start equals 0. And then print start, and then let's do. So in Python, we have to tell it that this start is referring to this start. Right. One second. So I'm calling it a goal. Print start, if start equals goal. Oh yeah, I'm not incrementing, of course. Okay, so this is another way of handling this issue where there's some information from one function call to the next that needs to be shared, from one invocation to the next. So so there are basically two ways of doing that. One is by having a global variable or something in like a shared outer scope, which is usually a bad idea. And the other is to pass that information. I mean, the only way to pass information to a function is by using a parameter. So we would do start, something like that, as we had it before.
Chad?
Yeah.
Can you explain the global variable again? Like, why didn't you put global start, the global keyword in front of start at line 21 as opposed to line 23?
Because it's already global here. So
okay.
I'm telling you, otherwise, if I don't do this, Python will think that start is a different variable.
We're not in a class. Okay. If we were in a class, then we could just put start, but since we're not in a class.
Right, you would do self.start or
Yeah.
class name, whatever, .start.
Okay.
But if we don't do this, then Python will think that start is a local variable to this function that just happens to have the same name as this global variable. But here we're telling it on this line, hey, if you see start in this function, it's actually this global variable. Okay. So that's kind of the very basic. So this is just replacing a for loop with recursion. Let's look at another example. All right. So one thing that that you'll see, I guess, yeah, maybe not fairly often, but one thing that you can see fairly often is the idea of a reducer. So you take in array of a whole bunch of different values, and you return a single value. So Python has a built-in function that actually has a few ways to do that. So let's say we have an array of numbers and we want to return the sum of all those numbers. So let's start by writing this. So we have a bunch of numbers. So if we wanted to sum all these numbers up, there's a few ways we can do it. We can talk about several of them. So does anyone have any ideas?
Is there a sum function?
Yeah.
Yeah.
So let's do. Actually, I'll just. Oh. So that works. So there's a built-in function. Sum, it'll take an array and we'll return the sum. Okay, what if we wanted to do this in a more imperative style?
What does imperative mean?
Telling it step by step everything it needs to do. Okay, so what if we use the for loop? You could loop over every single one of these and then add it to some other variable. So we could do something like total equals 0 for num in nums, total plus equals num. And at the end, I'm going to print num. Not num, total. Okay, so that gives us the same answer. There's also something, so JavaScript's higher order functions, you have map, filter, and reduce. Python also has a reduce, but it's located in the standard library. So we can use a reducer. So from func tools, import reduce. And then we can do print reduce. So reduce will take a function, takes two things. It takes a function and it takes the array, whatever you want to reduce. So you can use a lambda, or we could explicitly pass it in, but it'll take two parameters. So it will take basically it takes two pairs of values. So one ends up being an accumulated value, one is the current. So that will also give us the same thing. So reduce, again, it's a higher order function. So it will like map or filter. It will execute this function on every single element. The difference is that unlike map, which returns a new array of the same length, reduce will always return a single value. So here we're just saying, run this function, it'll compare two elements, it will add them together, and then we'll get a single value. Okay, so that's another way of solving the same problem. We can also use recursion. So how could we solve this problem recursively?
Could we just set it up as to add to the next number in the array?
Okay, let's try. So def we know that we'll need to pass in the nums. All right, so we want to write a recursive function that will sum every number in an array.
I think for your base case, you'd want to check and see if the length of nums is 1.
Okay, so yeah, the first thing we should do is decide, again, we need a base case and a recursive case. So our base case That will be if you're saying if the length of nums is 1. Okay. Oops, equals. Do you know what you want to do, or we can just put a placeholder there for now?
I guess print or return nums, because that'll give you, eventually that'll give you the sum.
Okay.
Return nums index 0.
Sorry?
Is nums a, nums is a, it'll be an array, right?
Yeah, nums is an array.
It'll come in as an array, but by the base case, it should only be one number.
Yeah, so,
Yeah, so-
we'll,
But it's still
Well-
an array. Oh, yeah.
Let's try to work through it as it is. I think we're gonna come into a problem, but it's a common problem. It's one so let's go ahead and do the recursive case. So what's the recursive case here?
You're gonna want to so call your some recursive function, but instead of but you have to like add the first nums to the second nums. Is that how we would start?
I think-
Yeah. So go ahead, Jim.
I was just gonna say, one thing is we need to return the function call.
Okay.
Like we can't just call it there. So we need to like return some recursive and then the argument that we're gonna pass. So since we're recursing, we need to like nums needs to change. So it needs to be, you know, a smaller, because our base case is the length of nums is 1. So when we recurse, we need to keep making the original array smaller.
Right.
So we could, let's see. I mean, on the line above this, I think this is one way to do it. So just after else, we could pop off the first element. So nums dot, well, we could set it to a variable. So like,
Okay.
I don't know.
All right, I guess last.
Yeah. Or yeah, that works.
yeah, the Python pop doesn't return a value, I don't think.
It
Oh,
doesn't?
No, I tried to use it the other day and it just
Oh.
removes it from the
Oh.
list. It doesn't return the value.
I think, I don't know. I've done it, I think I've done it before where like I pop and then I give it an index. So we could pop off the first one. We could call it like first num.
Yeah, it says it should return it.
Oh, never mind, I was mistaken.
But just like to make this make more sense, like to follow it better, I think if we just call it first and pop off index 0,
Okay.
I think that'll just be easier to understand as we walk through this. And then we need to pass first plus nums as the argument, I think.
First plus nums. So won't that just add it back to the array?
Can you add it to the new?
Oh, no,
zero?
yeah.
Yeah.
So we need to do return first plus some recursive nums.
Okay.
I think.
You're thinking we'll store the sum. What happens when you add an integer to an array?
I believe it will add it to it'll actually it's like append. So there's a couple things you could do here, but the main issue I'd like to point out is that we are giving it one piece of information, but we kind of need to keep track of an additional piece of information. Or at least one way of handling it is to explicitly keep track of another piece of information. Oh, I guess. Let's see.
Yeah, I'm messing this up.
So let's try doing 0. That may be. So this for sure, so when it's 0, nums will be nothing. So let's do 1.
So now if we're returning, we're storing
Yeah,
something
index 0.
outside of the array. Is that what's happening?
Yeah, so there are a few ways of solving this kind of problem. One is we're kind of, we're letting the information get stored in the stack, basically. So we're getting a value, we're changing whatever we need to change in order to keep the recursion moving towards the base case. That's this right here. And then we're adding whatever this ends up returning. So the first, let's not do 10, let's keep this simpler. Let's do 2. So this is going to get called with 1 and 2. If the length is 1, it's not. So first, we're going to pop it off. We're going to pop off 1. So this will be 1 plus some recursive, which we're going to call with this array of 2. And since the length equals 1, we're going to return 2. So this function at that point will equal 2. So it gets a bit weird. It's definitely hard to follow. And if we do 3, we'll look at the call stack as well in a sec. If we do 3, then we get 1, 2, 3. Let me put this down here. So 1, 2, 3. The length is not 1, so we pop this this 1 off. So this becomes a 1. So we do 1 plus some recursive of 2 and 3. So we don't know what this value is yet, right? We have to evaluate. We have to run this function in order to figure out what it is. So right now this is 1 plus something we don't know yet. We have to wait. So we're kind of on hold here, this first iteration. So first plus whatever this evaluates to. So we get 2 and 3 here. It runs through. Nope. So we pop off this 2. So first is now 2. And we have, for this particular iteration, we have 2 plus whatever the function call to this one is. But there's another layer in addition, right? So really it's 1 plus whatever this returns. So maybe I can write this out. So the first will be 1 plus some, oops. Right? And we don't know what this is yet. So there's another call. And that's going to end up being 2 plus some recursive 3 And then the third call is going to be 3 plus, well, actually, so some recursive, yeah. So this is actually just going to return the specific value that we have. So this will just return 3. The thing is that these are all kind of chained together now. So this one can't resolve until this one resolves. And this one can't resolve until this one resolves. So once this resolves, this last call, once we hit our base case and this actually resolves to a value, we can say, okay, we're done. We've reached the bottom. Now this is 3. So now this equals 3, right? So some recursive 3 equals 3. So we can replace this with 3. And then we can actually evaluate this. So 2 plus 3 is 5. And this call is the result of this. So now this equals this, right? So we can replace this with 5. And then finally, we can actually return a real value. So we evaluate this to 6, and then we can return this. So this first function call gets evaluated last, right? Because it's on the stack. So it gets put on the stack, the first function call, then the second function call, then the third function call. The third function call returns something, so that gets popped off. And then the second function call returns something, it gets popped off, and then the first function call returns the final value.
So in this case, the base case is the far end of the, in my mind,
it's the last one. It's the last thing that actually returns a value. So let me, so the first time we call it, we're kind of on hold, right? So we don't know. It's like saying, oh, hold on, let me figure out what some recursive 2, 3 is, and I'll get back to you. So it's 1 plus, hold on a second, I'll get back to you. Then the second one, we can pull out some value. So the second one is 2 plus, well, hold on, I'll get back to you. And then this final function call, because it's our base case, that's why base cases are important, it actually will resolve. And then once this resolves, it just sets off the chain, right? So everything can, the stack can unwind, or the stack, everything pops off the stack. Because now I'm not waiting anymore. Now I know what some recursive array 3 is. It's 3. So now I can finally, like, that block is removed. I can evaluate this 2 plus 3. And then this guy finally, oh, well, now I know what some recursive 2 plus 3 is. It's 5. So now I can evaluate that, and then this returns, and so on. So let's look at the debugger so you can see the call stack. So this stuff is, if you don't already know how recursion works, this is I wouldn't anticipate learning it on your first exposure. If you do, that is wonderful. So I'm gonna call this function here. And we can see our call stack, we have some recursive, and we can look at the call stack for the contents of this particular execution context. And that's the array that we pass in, 1, 2, 3. That makes sense, right? So we keep going, past the if, we pop something off. So now we have this first variable, and we're going to return first plus some recursive. So let's see what happens. So we have another stack, right? So some recursive, we're not quite sure what to do. So we're gonna have to wait to evaluate this until this one evaluates. So some recursive, the second call is gonna go and do the same thing. And then it's gonna have to wait for this one. So this one is dependent on this one, and this one is dependent on this one. So now we're here. we're going to hit our base case, and this is actually going to return. So we can pop that off. So we pop it off, and now because it returns, we can actually evaluate this one because there's a specific value now. So this gets popped off, and then that gets popped off.
So looking at the notes about recursion in the inception example, that's basically when they set off all the charges. Oh, spoiler alert if you haven't seen the movie.
I saw that movie.
Charges, and then they pop up all the dream states.
Yeah, I mean, I actually don't remember. I didn't write that document. That was John. But yeah, so I mean that would be, so whatever chain of events sets everything else in motion. It's that final base case. It actually resolves. It stops. I have a real value. So yeah, you can think of this as blowing stuff up.
All right, so every iteration in the call stack saves the number in first, and then that's where it all gets added at the end.
Yeah, so everything in the call stack will have, you know, a first value. This will be first, and then depending on what it's doing, it might have to wait for this. But it's saying it's plus this. We just don't know what this is.
And all of those firsts are independent of each other.
Yeah.
So how, if you wanted, I don't know what the use case would be, but could you have a variable that that would stay the same, or I don't know. Let me figure out what that question is.
Sure. So this is one way of doing it. I want to show you a slightly different way of doing it as well. We'll comment this out. And then, so I'm going to pass in another, so we can hold this, we can pass it along to every single call. So ultimately what we want is the total. We can do something like total. Then return. Nums one, and this should give us the same result. No, what am I doing wrong? That's the other way. Sorry. So, you know, a slight variation. Here we're kind of, this function call, we're actually evaluating a value every time. This is just another way. In some ways, I think this is a little more intuitive, maybe.
Okay, so that's how I was looking at it at first. But since the call stack will store it on its own, we can really just skip storing it in a variable like that. Is that the point of recursion?
I mean, both of these examples are recursive. This is just, yeah, this information is getting stored on the more on the call stack. And here the information we want, we're kind of evaluating it at every function call.
Okay.
But these are, I mean, yeah, it's basically the same thing. So these are both recursive functions. Okay. I want to show, how long have we been doing this? Since the last break? It's been half an hour?
I think we're approaching an hour.
Are we? Okay. Then let's take a break. Let's take a 10-minute break and we'll go over one slightly more complex example. All right, so we're gonna do a slightly different example here. And so this is, contrived and pretty silly example, but so let's say that, it's Halloween and, your friend has gone trick-or-treating and he's got a whole bunch of M&Ms. And so you want to do like a, one for you, two for me kind of thing. So what we're going to do is you're going to divide, you're going to take all these M&Ms that he has, in this case, start with 10, and we're going to divide it in half. And if there's any remainder, then you'll take the M&M and then you'll take whatever this half of the pile is and you'll divide it in half again. And if there's any remainder, then you take it and you'll keep going until there are no M&Ms left. So if we think about this, this is a kind of problem that suits recursion, or we're just repeating the same thing over and over again until we reach some base case, which in this case is 0 M&Ms. So we'll start by dividing this in half. So we'll take 5 and put it over here. 1, 2, 3, 4, 5. So we have 5 M&Ms in here. So you've divided this in half. So this pile stays here. And now we have a new pile. And there's no remainder, so we don't get any M&Ms this run. But we're going to follow the same procedure. We're going to take this pile and we're going to divide it in half. Well, 5 divided by 2, if we exclude the remainder, is 2. So we'll put the remainder, this is our pot here, and we'll divide this in half. And then we're going to follow the same thing again, right? We're going to take this pile, we're going to divide it in half. There's no remainder, so we don't get any M&Ms. Then we take this pile and we divide it in half. So we get this last M&M. So now we have 0 M&Ms, and this is our base case. So this is the basic idea. So we want to implement this in code. We start with a pile, and then we divide in half, like whole number or integer division, until we reach 0. So let's write a function. And we're going to start with, let's just say, the number of M&Ms. And for now, we'll pass and we'll do, we'll print it. We'll start with 10 M&Ms. So what are the two things we need to figure out first?
Base case and recursive case.
Okay, so let's base case. Let's just go ahead and write these out. All right, so we have a base case and a recursive case. So what should our base case be?
If M&Ms equals 0.
Okay. So if num, maybe we're not quite sure what to do yet. And then our recursive case.
anything else run the function again?
Yeah, so what we're doing, the procedure we're following is that we're taking a pile and we're dividing it in half. And that's going to be the source material for the next round, right?
So would you find that remainder and pull that out first before you run the recursive case?
Yeah, so what are we going to pass as a parameter to the next call of this function?
You're going to be passing the number of M&Ms that's left over after you remove the remainder.
Yeah.
It's divisible by 2.
Okay, so let's do, I don't know what the official term, it's not always going to be half, but we'll just say, so we'll do num M&Ms. And so this is going to give us a whole number. So 5 divided by 2 is going to be 2. The remainder is going to get chopped off. Okay, so we can call this. We'll do this. Okay, and then, so if we pass in 10, we'll start, this will be 10. This will fall through. So this will be, half will be 5. We'll call it with 5. Then we have 5 here. This is, passes through. 5 divided by 2 will be 2. So you're calling M&M with 2. This passes. So 2 divided by 2 will be 1. So we call this with 1. Still passes. And then 1 divided by 2 will be 0. So we call this with 0. And then this is 0. And we're done. So I'll just do something like, oops. So we can try running this. So this print statement is printing none because this is returning none. But we can see that we don't have an infinite recursion, which is good. I mean, that's a good sign. We're not recursing infinitely, but we're also not really, maybe not really getting any information. So let's say that what we actually want to return is kind of the history of all of these calls. So let's say we want to return something, an array, and we want to return the remainder that we got for each call. So the first time we call it with 10, so 10 divided by 5 is even, so we get 0 the first time. Second time we call it with 5, and 5 divided by 2 will be 2 with a remainder of 1, so we get 1, right? We call it again, that's 2, it divides evenly, so we get 0, and then the last time we should get 1 M&M, right? So what we want to return is something like this. So there are a couple options. Let's go with a default parameter in this case. So what I'm going to do is and I could do this, but oftentimes you don't want to you don't want a mutable data type as a default value. So I'll do none. And then I'll just set it in here. Okay. So now I've given it a default parameter. So I pass in 10. And what I want to do is not just decrement, which is good. We need to. It's going to work us slowly towards our base case. We need to do this. But we also want to keep track of the remainder here for each call. So what we can do is we'll append so instead of, we'll use the modulus to get the remainder. So this will basically be 0 or 1 every time. And then in this next call, in the recursive call, we're going to need to pass in my take. So let's, before we take another step, let's just run through this. So we call this function with 10. This is 10, and then my take will be none. Then my take will be this empty array. This will fall through. Half will be 5. My take will append 0. So, sorry. Yes. So sorry. 10 modulus 2 will be 0. So we'll call this with 5 and this 5, and my take will be this. We call it again. So my take will have a value, so it won't be none. So this will skip, this will skip. We'll get 2. So 5 divided by 2 will be 2. And then we'll take this and we'll append it. So 5 modulus 2 will be 1. So now my take will look like this, and we'll pass in 2, and then this array for my take. This will fall through. Again, this will be 1. This will be 0. So we'll append 0, and then we'll call this with 1 and whatever this is. So here, this will fall through, 1 divided by 2, this will be 0, and this will end up being 1. So we'll call it with 0 and this. This base, the base case hits, and we'll print done, and let's just return my take. So let's try running this. And we get this as a return value. So are there any questions about this?
So in this case, the base case is the last thing that happens before the return. It seems like there's 2 types of recursion. It either goes up and then back and the base case is over here, or it just goes up and the base case is hit and it returns.
Yeah, so because we're passing in this updated value every time, it doesn't, the unwinding of the stack doesn't, it doesn't quite have the same role.
Would it still unwind? It just doesn't matter.
Well, it will unwind, but the value will be, so this first call is still waiting. So let's look at the call stack. So we'll call it. So this first call is on the call stack. So now we're going to return, but we don't know what the value is going to be yet. We still have to wait for everything else. So we still have all these values. So we don't know, this return value is still basically hanging on So in every stack, this return value is hanging on. We still have the case where we need to get to the very end. So we still have all these stacks. So this first call is still waiting for this return value. The difference is once we actually hit our base case here, the return value is basically going to be the same for every. This is going to return the value is basically just going to get passed along.
So it's being updated as it goes further down the stack rather than being updated as the stack unwinds.
Yeah. So I wouldn't think of these like these two different ways of doing it as they're both recursion. And they both have to wait for all of the, they build up a call stack and then they unwind.
So that return after, or that return in line 7 is still not returning to the end of the function or the whole thing. It's still returning to the recursive case.
Yeah, so this one won't return until the very last call of this one. So again, it's the same thing. So we have the first call, and then the second call, and the third call, and then let's say, the fourth call, this will actually return. And then because that returns, the result of the previous call will also return. So that one can get popped off, and then the same thing happens again until you pop off all of everything on the call stack.
I did some reading about JavaScript callbacks. Is this similar to like a JavaScript callback? Is this similar to that, or?
So I mean, I guess in some ways it's similar in the sense that you're gonna have two things on the call stack. But it's different. It's like a one. I guess you could think of it as like a single depth recursion. So I call a function and then I wait for something else to happen. Once that happens, then I call this other function. But I mean, there is that similarity, but they're really different kinds of things.
This would work if we removed half and put the num M&Ms divisible by 2 into the recursive call.
If we just put this directly into the call.
Yeah.
Yeah. So that would also work. Just for the sake of readability, I put it there, but yeah, this also works. Okay, so let's try building on. So now we have this array of values, but I don't know how many M&Ms I'm going to get. So I have the history of each round basically, but I want to know, I want a final number. How many M&Ms am I going to actually get? If only we had some way of summing recursively all the elements of an array.
Just import your sum module.
Okay, I guess. All right, I'll just.
Yeah, we could.
Yeah, and enthusiasm is waning. I know it's a long day. So we'll import this one. And let's do So we get 2 M&Ms. And also, I won't, so I have one other one, but just, we won't have to write it, so we can wrap this up. You guys can give it a little break. So here's another, so let's say I wanted to know what's the optimal number of M&Ms to start with, so I can maximize my take. So you can also figure that out recursively. So we have our basic M&M. So we actually get our history, and then we can add up everything. And then we can call this get optimal function, which will start. So I'm using all these default parameters. So you have to watch how much you can't go above, 900 and something. And then I have all these default parameters, and then I say if the total is greater than the biggest take. So let me just show how it's implemented here. Yeah. So let's start with 10. There's that coming from line 23. Empty list. Some recursive is getting called in line 34. Line 34, and that's getting called from get optimal in line 40. So the first time we call it, num is 10. Res is M&Mi, so it's 0. Okay, so this is just because we have a slightly different implementation. So let me take this one. So what this is doing, it's gonna run through the numbers 0 through whatever we pass here. So this would be the number of M&Ms in the pile initially. And then it's gonna figure out, it's gonna run all these other functions. Again, this is all being done recursively. And it's gonna say, if you start with 7, you'll end up getting 3 M&Ms. And if you start with 800, so this will check everything from 0 to 800. What's the best you can do? Looks like the best you can do is you can make 9 M&Ms if you start with 511. So this is just kind of silly. I wouldn't worry about this. I just want to show you that you can use recursion to do, everything basically. Not that you really should. You shouldn't stop using for loops or anything, but.
Chad, you said this is preferred for functional programming. Can you just say something about how this relates when we're doing object-oriented? Is it still something we would use all the time, or?
Yeah, you can. I mean, you can use recursion whenever. So these problems are not necessarily like they don't scream recursion at you. We're basically like iterating. You can easily, I think, and more intuitively solve these issues with for loops. But there are some problems like the towers of Hanoi. There's a couple other harder recursion problems that are actually easier to solve using recursion. Recursion is just a better fit as a solution. So I wouldn't try to do things recursively or anything like that. And I mean, if you're learning about recursion, then sure, you can try to shoehorn in some recursion, but as a practical matter, I wouldn't. I think the common sense advice would be avoid recursion unless you have to use it. It's it's the kind of thing you get asked on an interview question and the kind of thing that you never actually implement.